Welcome to week 11 of our medical software class, and in this week's lectures we'll focus on artificial intelligence and machine learning, the use of these technologies, the challenges they produce as we integrate them into software, and the whole aspect of how one regulates these things. How do we create rules to ensure that the use of such techniques results in safe software that doesn't endanger their users and our caregivers. So these are the goals of this week. We'll introduce what machine learning is, we'll discuss deep learning, and then we'll talk a little bit about the regulatory aspects of the use of artificial intelligence machine learning in medical software. And finally, we'll touch a little bit on artificial intelligence machine learning as part of the software lifecycle. So I made the decision as we designed this class not to sprinkle AI/ML throughout the last 5 weeks, but to save all those issues for this segment here. So we have 6 segments. The first 2 are the basics. We'll introduce AI/ML techniques, and then we'll talk a little bit about the evaluation of machine learning methods and related issues. Then we'll introduce deep learning. Professor Nishat Vornik will come and give a presentation on that. Then I'll come back and talk about the regulatory aspects. First, an overview of the regulatory guidance from other countries, and then we'll do a deep dive into the Singapore guidance for AI/ML, which is one of the better documents that's out there. And then finally, Professor Onofri will come in and talk about AI/ML and the software lifecycle. This week's material is spread all over the textbook. There's some in chapters 8, chapters 9, and chapter 15, but you can track it from the index if you want to do more reading on this topic. So let's get started. Let's do an introduction on artificial intelligence and machine learning. What do these terms mean? What do they are? And these terms are somewhat confused. You'll hear them used interchangeably. People who have a long background in computer science have very specific meanings for them. Others just use this term more loosely. And so we'll try to give some definitions, but please realize that the use of these terms is far from consistent, and you'll hear people use them interchangeably or use slightly different definitions as we go. So here's one set of definitions from John McCarthy from Stanford, one of the fathers of this field. AI is defined as the science and engineering of making intelligent machines, especially intelligent computer programs. So if you think about AI, it's the superset. You can see the big green oval on the right of the screen. AI can use different techniques, such as ML, machine learning, to produce intelligent behavior, including models based on statistical analysis of data and expert systems that primarily rely on if-then statements. So ML is a subset of AI. In this paper, and this is a usage we will use here too, we refer to an ML system as a system has the capacity to learn based on training on a specific task by tracking performance measures. And then the final statement here, AI and specifically ML are techniques used to design and train software algorithms to learn and to act on data. And finally, deep learning, which the other term you will hear, is one particular machine learning technique, although it's by far the most popular right now. So when people think about machine learning and AI, for all intents and purposes, right now they're thinking about deep learning. Deep learning has taken over this field. And so the definition that I would like you to think about when you think about ML, it's a technique that lets you learn a relationship between data. So given the input, it can predict the output. So it's a prediction mechanism. It's a learning mechanism that learns patterns. It learns if I give you an image and if I give you a set of images and a set of diagnoses for, say, cancer patients, I learn a relationship so I can predict the diagnosis from the images. So when I give you a new image, you can get a prediction for a new diagnosis using this algorithm. That is the essence of what machine learning is right now. This is the informal definition that you'll hear out there. This is from a tweet by Matt Veloso. And the difference between machine learning and AI, if it is written in Python, it is probably machine learning. If it is written in PowerPoint, it is probably AI. What he's referring to is that the people who work in the field and do hands-on work called machine learning. People at the business level and consultants and people like that call it AI. So you can almost hear from the vocabulary that gets used what the person's background is. So that's kind of another interesting comment. If you came up through the traditional engineering schools, through electrical engineering, your introduction to this field would probably come from this book, Duda and Hart. This goes all the way back to 1973. And this is the other name of this field. It's called pattern classification. The book is called Pattern Classification and Scene Analysis. So people who come from an engineering background think of machine learning as a successor or even just a renaming of what was pattern classification. And historically, we would not have thought of it as part of AI. But, this is just arguing about names. This is a good classic book. If you can get your hands on it, it's a great read, even 50 years later. So of the many kinds of machine learning there are, we will focus on supervised learning. This is the fundamental technique that we're dealing with. And in supervised learning, we have an input, X, perhaps images. We have a function, F, perhaps a neural network, and we have an output Y, maybe in this case a diagnosis. So let's walk through the steps. We have a training phase. Given training data pairs X, Y, so images plus associated diagnosis perhaps, we learn a function that takes X and maps it to Y. F can be any kind of function, but typically these days it's a deep neural network. And what we're learning here is F. So when we say the system learns, it learns this function. It learns the parameters of a deep neural network. And then we have the application phase. In the future, we get a new X, let's call this X prime, and we use the existing F, the one that we have trained here, to estimate a new Y, Y prime, which is the application of the function to X prime. So we are estimating Y prime. So in the training phase, we learn F, and in the application phase, we're estimating Y prime. So when you design software that uses a machine learning technique, outside of the actual software, you have a separate set of code that learns this function F. This gets stored and gets incorporated into the software, which in the application files just applies that function F to estimate the new Y. The hard part in all supervised learning is getting hold of the training data XY. This often requires experts to label the input data X to generate the target outputs Y. So for example, in the example I just gave above of images plus diagnosis, you get to get a lot of images and have experts read through them, confirm the diagnosis so you can build your training set that you can now use to train your algorithm so that it can be applied in the future. The two most common machine learning applications are classification. Given some input, we output the class belongs to, for example, healthy versus diseased, cancer versus non-cancer, something discrete. And then regression. Given some input, for example, time spent studying, past grades of a student, we predict some output, perhaps the test score. And regression is a continuous function, and really one is categorical and the other is continuous. And while in textbooks these are treated differently and there's some interesting mathematics that are separate from them, if you actually try to implement these things with deep neural networks, the only real difference is almost the last layer of the network. The rest of it may almost be the same. It's just what is the evaluation criterion? It's different for a discrete versus a continuous function. But other than that, the two things may almost be the same thing. So let's talk a little bit about classification as an example. And let's cast it in a little bit of a more traditional sense before the deep learning era here a little bit. So given some measurements, which we'll call the descriptors or the features, we assign a label to these measurements. This is our goal. So it's a two-step process. Given a thing, we map it into measurements or features. This is the representation. So if we have a person, for our purposes, we reduce the person into two measurements, their weight and their height. If we're trying to figure out if this person is overweight or healthy, height and weight are actually a pretty good description of a person. Given these measurements, the features we classify. So we take weight and height, and we output a value either healthy here or overweight. Now, it could get more complicated, but let's stick to this classification for our example here. So how does this work? Let's assume that now we're back to, say, 1975 perhaps, and let's think about how the machinery of this process would have worked. So here are healthy subjects. We have a set of healthy subjects. So we have their heights and weights. So this is a single subject here with this height and this weight. And some expert physician has classified this person as healthy. And this applies to all the green ones, they're healthy. All the red ones are overweight. And you can kind of see that they have high weight, low height. That is a typical definition of being overweight. And then what we're going to do here is we're going to learn a line in this two-dimensional plot that separates the healthy on the top here from the overweight on the bottom. So if we bring in a new subject and you happen to land here, we'll classify you as overweight. If you happen to land here, we'll say you're healthy, and that is the process. So we assume, and this is a fundamental aspect here, is that an expert has already labeled the subjects as healthy or overweight. And this is the hard thing about machine learning. People talk of machine learning as magic, but the fundamental problem in machine learning isn't the math. The math is actually often fairly straightforward. It's getting access to these data pairs, the inputs plus the labels. That is the hard thing. And that is why all these internet companies, you look around, the Googles, the Facebooks of the world, are vacuuming data like crazy, because it's the data that actually defines the performance of this algorithm. So let's see how we do this in practice. This is the simplest algorithm. It comes from Duda and Hart. This is all the way back to the early 1970s. We compute the average for each class. So this green circle is the average person here, average height, average weight of the healthiest. This red circle is the average height, weight of the overweights. And then we find the line that bisects the line connecting the average. So that's, to put it graphically, you connect the averages and you find the line that cuts this line in two. and anything below that is overweight, anything above that is healthy. So if we take this algorithm and apply it, so now we're in the application phase. All we have is the line. This is what we have learned. This is our F from the previous consideration. Now here comes a new subject. They land there. Based on our algorithm, it's above the line. We classify it as healthy. Here's another subject. It's below the line. We classify it as overweight. A third subject, they're healthy. A fourth subject, they're overweight. And that is essentially the process of using machine learning. You train based on data. You learn a function. You keep the function. And then you apply it in the future. That is a concept here. One interesting aspect, and this is very similar to what we saw earlier when we talked about parametric versus non-parametric estimation for probability density functions, is this distinction between parametric versus non-parametric. In the previous example, we just learned a line. That's a parametric function. It's just a line. We learn two parameters, and that's fine. You can also learn non-parametric functions that learn a lot more from the data and actually are implicitly defined as opposed to explicitly as a parametric function. So let's take a look at an example here. So before, just to recap, we assume a formula for a boundary line. We learn the parameters of the line. But what if we don't know what the shape of the boundary should be? Sometimes we can't tell. So how do we do that? And the oldest method in the book is nearest neighbor. So here's a set of data. We keep it all in memory. When the subject comes in, we ask the question, is the most similar sample of those we have in memory healthy or overweight? And we use this to classify. And if you think about this, this is how we often do many tasks in life, and this is what doctors often do when they do diagnosis. You look at a patient and you say, okay, what patient does this remind me of? And you find the most similar patient in your long memory of seeing previous patients, and you say, okay, well, that was the diagnosis, so chances are this person is going to have a similar case. So let's formalize it a little bit and just show you what the decision boundary looks like. We have the nearest neighbors. We have the samples here. Red are the overweight, greens are the healthy. And if we have this kind of separation, we end up with a boundary like this. So on top, you're healthy. On the bottom of this, you're overweight. So this irregular curved boundary. Now, what if we have one more sample in our database? That person up there, despite appearances, is actually overweight, even though they appear to lie on the healthy category. We don't know. There may be something genetic about them. So now our boundary becomes this discontinuous function. Below here or above here, you're overweight. In the middle, you're healthy, if we continue with the previous analogy. When it comes to neural networks, which are a lot more complicated, we end up with many, many islands. So we could have an island here, an island here, an island here. So we divide this area into almost a checkerboard type pattern with healthy and overweight, or the two classes interspersed. And an extension of this technique is k nearest neighbor. So instead of looking at the nearest neighbor, we look at the nearest k, where k could be 3, 5, 7, and we do majority vote. So we find of your 5 neighbors, if 4 were healthy, you classify you as healthy, and so on and so forth. So to conclude a little bit, let's just raise some problems. All so far sounds very good. We almost never have enough samples, especially when we're dealing with high dimensions. So far we've talked about height and weight, a 2-dimensional description of a person. So if you think about my grid, I can have enough to fill in a grid. So if I want 10 points along the row and 10 points along the columns, maybe I need 100 subjects, and that's a reasonable number. Now, if I'm doing a higher level classification where I have 8 features, all of a sudden now this blows up to 10 to the 8, and all of a sudden I need millions of people to fill in my space. So you can imagine very quickly we run out of the ability to have enough samples as the dimensionality goes high. The other big problem in machine learning is that we can overlearn from our samples. What if one subject or a small number of subjects is strange? So think about k nearest neighbor, and if you have a bad subject there, somebody who is misclassified perhaps, now that person is going to propagate throughout your result process. The training data can be mislabeled, which is the previous problem. There could be just transcription errors potentially, and the dimension can just be too high. People like to use lots and lots of features. It feels better to have a richer description, but if the dimensionality is too high, that can get you in trouble. And the correct answer, and this is the fundamental problem in machine learning, is only known on the locations of our samples. We have no general truth, right? We only know the answer at those 20 locations where we have training data. We're trying to interpolate in that empty space, but we have no idea what that function is. And just to give you a little bit of a different view of the topic, we have another clip from Professor Christian Kastner from Carnegie Mellon University. We'll talk a little bit about this issue.
In machine learning, we have example data. We feed the example data in. We see how often do we get the expected output. we measure accuracy or many other metrics in this area, recall precision, efficacy, whatever. And we get some percentage typically, and we kind of see how close do we get to what we want. We don't usually know for arbitrary inputs what we're expecting. So kind of the way that we're writing test cases is not the same, how we can pick examples. We typically select a representative sample of data that we're testing on. We're not really looking at corner cases as we might do in software engineering. If one prediction is wrong, that's not the end of the world, right? We accept it, it's just lower accuracy. In the end, what we're looking for is not really correctness of the system, because we don't really know what correct means, right? Traditionally, correct would mean all the answers are right to some standard, to some specification. We're kind of looking for fit. A nice saying here is all models are wrong, but some models are useful, right? So what we're looking for, is there a model that's good enough to be useful in practice, that works most of the time or in a sufficient number of cases? There might be some hard problems where 10% accuracy might actually be much better than we had before. And there are some problems where 99.9% accuracy is not acceptable because it's not useful for the problem.
And that is the actual point here. When we resort to machine learning techniques, it is often because we have no other way of getting at an answer. We don't understand the problem. We learn from examples, and we have to take all these other issues that come together. So we hope to find something that's good, that works most of the time, and depending on how serious the application is, that number goes up and up as we go. And then, as we'll see towards the end of this week's segments, we build in safeguards around that, so when things go wrong, we can detect them and pull in a human expert to do correction. So with that, we'll stop this segment. In the next segment, we'll discuss a little bit of the issues of how these things are tested and some of the problems that occur in these very data-driven algorithms. Thank you.